Hello to everyone. Today we have the great pleasure to have Gerald Dunne from the University of Connecticut, who will tell us about Resurgent trend series in Hopf-Algebraic Dyson-Schwinger equations. And so let me remind everyone that the talk is recorded, so you may ask questions during the talk, but please remember that you will be recorded. You may also use the chat to ask questions. Okay, Gerald, please.
Okay, thanks very much. Thanks, Kurush. Thanks, Frederic. So I want to talk about some recent work with Mishi Burinsky and also with Max Meinig, my student, about trying to disentangle some non-perturbative information out of this Hopf-Algebraic structure in quantum field theory. And some background work here is related and motivated by some recent work with Ovidio Costin also. So let me start with some motivation because, I'm a physicist. I think a lot of people in the audience are mathematicians. So I'd like to at least convey the basic idea and the motivation, if not all the technical details. So we know very well the work the Kreimer and Connes relating perturbative renormalization in quantum field theory to a Hopf-Algebraic structure. This is interesting mathematically, and it's also enables some perturbative computations to very high order, which is a very difficult thing in quantum field theory. And this method has spawned a lot of new techniques and new ideas that have enabled quantum field theory calculations to advance quite dramatically. On the other hand, there's also this work of Ekal and collaborators and followers in what I would call resurgent asymptotics, which to a physicist means the following. It means that if you're given a perturbative formal series, which is typically asymptotic and divergent, there's actually some more information hidden there, which is what we call non-perturbative physics. And the combination of the two is something called a trend series. And from the physics point of view, the interesting thing about this is that there's some extra information encoded in the perturbative physics, the perturbative formally divergent series. And learning about that and the way these are connected is a very active question at the moment in physics applications. So the basic idea underlying what I want to talk about today is to try and use this structure of resurgent trend series to learn about non-perturbative properties of quantum field theory and combine this Hopf-Algebraic structure with this resurgent asymptotic structure and see what happens. Just a side comment that may not be obvious to everyone is that the connection between these perturbative and non-perturbative physics are most efficiently and most clearly understood at higher orders of perturbation theory, which means that if you're going to try and do this in quantum field theory, you need a way to get to higher orders in perturbation theory. Just doing low orders in perturbation theory is not enough. And that's another reason why this Hopf-Algebra method is so appealing, because it's one of the few methods that does enable you to study high orders of perturbation theory. So by the way, I invite people to interrupt if I use some jargon or physics terminology that's unfamiliar. So in particular, I've already used the word non-perturbative many times without telling what it means. So that's what the next slide is. What do physicists actually mean when they say the word non-perturbative? So I remind you that in quantum mechanics and in quantum field theory, perturbation theory is extremely successful. It's one of the standard techniques. However, it's typically divergent. Now, there are well-known ways to take care of that and to extract information, Borel summation and variations thereof. In particular, the Ekal-Borel summation is a particularly powerful technique. But perturbation theory is only part of the story in physics. And let me give you an example. There's an effect in physics called the Stark effect, which was awarded the 1919 Nobel Prize, where you take an atom which has some known energy levels for the electrons, take the hydrogen atom, for example. Now apply an electric field to that atom. You've applied an external perturbation, so the energy levels in the atom have changed slightly, and you can calculate the energy levels as a function of the applied field using perturbation theory. And this is a standard exercise in the first course in quantum mechanics to calculate the first one or two corrections in perturbation theory. If you look at it more deeply, not in the first course in quantum mechanics, you learn that this series continued to higher orders is only a formal series. It's asymptotic. The coefficients here, these E sub n coefficients, they're just numerical coefficients. They grow like to n factorial. So that means to make sense of this, you need, at stronger applied fields, you need to employ some of this Borel summation technology. But there's also something more interesting lurking here, which is that there's also a non-perturbative effect when you apply this electric field to the atom. Not only do you shift the energy levels slightly according to this perturbative calculation, but you can also ionize the atom, which means electrons are ejected from the atom. Bound electrons actually escape from their bound levels. And that's characterized by the fact that the actual energy of these electrons has this perturbative contribution, which we just computed, but it also has this term which is exponentially small. It's e to the minus some constant depending on which atom and which energy level we're talking about, but divided by the electric field. And it's also multiplied by a formal series. Since this thing here cannot be expanded in powers of the electric field, we call this non-perturbative. And this is what physicists mean when they say non-perturbative. Many problems in physics have this structure, that there's some perturbative solution, but that's not the whole story. There's also these interesting effects here which correspond to things like decay or ionization. Now, the thing that physicists find particularly interesting about resurgence and resurgent asymptotics is that these two things are related at a very deep level. This formal series here is actually related to this formal series here in a very profound way. And these dot, dot, dots here refer to higher orders of the squares of these exponential terms. And all of these are related by something that's called the bridge equations. And they're quantitative relations between perturbative effects and non-perturbative effects. And those are some of the most interesting questions from the physics point of view. And so the basic theme of what I'm talking about today, if you remember nothing else, is that it's well known now that at this level, at this perturbation theory level, Hopf-algebras are very important. But if you invoke resurgence, the Hopf-algebraic structure here should be upgraded to the Hopf-algebra structure here and here and here and here. And the question is, what are the Hopf-algebras here? And how are they related to the Hopf-algebras here? That's the question I want to ask. And I'm going to show you in two very specific cases how we can understand how this Hopf-algebra structure leaks into these higher order terms. Okay? So I could stop my talk here. I've said everything that's important, but let me continue and give you some more background and some examples. So resurgent trend series. The description I'll give is based on these ideas formulated by Écart, but this goes all the way back to Stokes in the mid-1800s. Resurgent functions are generalizations of analytic functions that are closed under essentially all operations of analysis. So that means that we can control things like Borel transformations, we can do analytic continuation, we can do Laplace transforms. These are all operations that we can't necessarily do on some formal expansion without some more technical machinery. And underlying all this is this really remarkable statement that these resurgent functions can be generated from just three basic building blocks: powers of some small parameter, these exponentially small terms, which I would call non-perturbative terms, and logarithms of this small parameter. And iterations of all these objects build a general trend series. In physics applications so far, the most natural type of trend series that we come across is something that I'll call a semi-classical trend series, which includes what I would call perturbative fluctuations, expansions, formal series expansions in some small parameter, but also possibly these non-perturbative exponentially small terms, and also powers of logarithms. And I'll show you some examples of how this arises. And the new feature that's particularly interesting is that whereas a formal asymptotic series only tells you something about the function you're trying to study in some particular direction, or maybe some particular wedge in the complex X-plane, once you include these other transmonomial elements, in principle, this object, this combined object, this trend series, has encoded in it all the analytic properties of this function. So it's much more efficient, much more information stored in this trans series than just in the perturbative expansion. For that to work, there absolutely must be connections between these coefficients for the expansions in the, say, the perturbative direction or the non-perturbative direction or the logarithm direction in order to encode all this analytic continuation properties. So this rich structure between the expansions, different types of expansions, are again a manifestation of these so-called bridge equations. Now, this structure came out of the world of differential equations, so there are rigorous theorems in the context of differential equations. There's very compelling evidence in quantum mechanics and matrix models in physics, and there's also, it depends on your level of rigor, but there's also strong evidence in some contexts in quantum field theory and string theory. And as a theoretical physicist, I'm interested in trying to explore applications of these ideas in physical contexts. So the word resurgence, I've used it, it may not be familiar to people, it may be, I'm not sure. Let me at least give you a visual image here that these raindrops are supposed to represent different critical points, different saddle points, different expansion points of different singular points of the particular problem you're studying. And you may be able to make expansions around these different saddle points or critical points. And the ripples are supposed to represent those fluctuation expansions around those points. And the basic idea is that if you know some information about the expansion around some particular critical point, from that, in principle, you can deduce information about the expansions around the other singular points or critical points. So these functions resurrect or surge up again at these other points. Now, this is a very big statement. It's a very grand conjecture that these trans series somehow arise in all natural problems, which itself is a somewhat vague statement about, but roughly speaking, things that we study coming from a set of specified differential equations or integral equations should have this general structure. Now, a little bit of physics to start off. Now, some background motivation about the Feynman path integral. So the basic idea of Feynman was that we could describe the transition amplitude from some position in space to some other position in space at a later time through the so-called amplitude, which is a sum over all the paths going from the initial point to the final point, weighted by a phase factor involving the action for that classical trajectory or for that trajectory. And so this can be viewed to the mathematicians and the audience as a generating function for Feynman diagrams, if you expand this according to some perturbative expansion of this action. When we come to quantum field theory, the idea is very similar. Instead of summing over paths, we sum over all configurations of fields that are now functions of space-time, whereas here we've got paths, which are functions of the time parameter. And there's an action parameter here, action functional here, functional of the fields. And there's maybe some coupling constant in place of the Planck constant. So likewise here, this basic, extremely ill-defined mathematical quantity can be interpreted just as a formal generating function for Feynman diagrams. And through the work of Dirk and company, we know that there's a very rich combinatorial, algebraic, and graph theoretic, and also number theoretic structure underlying this formal expansion in terms of Feynman diagrams. It's for something that's ill-defined mathematically, it's extremely good at producing well-defined mathematical conjectures and problems. But as a physicist, there's another way to interpret this Feynman path integral. If you were confronted with an exponential integral like this, never mind what the measure here actually means, another way to approach this thing is to look for stationary points of the action and view this as a steepest descents or stationary phase approximation to this formal generating function. If you do that, you generate, instead of a perturbative expansion, you generate what we would call a non-perturbative expansion, because once you evaluate the action on some critical point, which would be some solution to the classical equations of motion, you of course generate something that's e to the I o divided by the coupling. So this is non-perturbative in the coupling, times the action evaluated on that critical point. And then the fluctuations around that saddle point will generate some formal series. So this is a way to arise at this type of structure, starting from the path integral rather than this type of structure. And the basic idea is that if this path integral is to make any sense whatsoever, these two things should be related somehow. And so for ordinary exponential integrals, we understand this very well. This goes back to the work of Stokes on the Airy function. That the Airy function, of course, has asymptotic expansions that we understand, but it also has perturbative expansions that we understand, and we understand how they're related to one another. So the underlying idea here is to view this Feynman path integral as actually a generator not just of a perturbative series, but as a generator of a trend series. And I claim that if you can understand a field theory in that way, it leads to new insights into the structure of the field theory and also new ways to compute things. So that's all very well, and it's easier to explore this at the level of quantum mechanics, and even there in the level of quantum mechanics, some interesting new things have been learned in the recent years from this perspective. But an important difference between quantum mechanics and quantum field theory is that in quantum field theory, we have this extra level of divergence to confront, which goes under the name of renormalization, which roughly speaking says that even at a given fixed order in perturbation theory, the Feynman diagrams that you would like to calculate at some fixed order in perturbation theory are themselves divergent. And there are physical reasons for that, and there's a whole machinery developed to implement that procedure. And it has this nice Hopf-Algebraic and graph-theoretic structure. But that's even before you come to the problem of trying to resum all orders of the perturbative expansion. So there's been recent progress, numerical, semi-classical, which is basically this, a phrase physicists use to describe this saddle point, steepest descent approximation to the path integral. And here I'd like to see what we learn if we invoke this Hopf-Algebraic structure for perturbative renormalization of quantum field theory and try to extract from that the non-perturbative information about the field theory using these ideas of trend series. So there are a couple of questions in the background here. First question is, these Dyson-Schwinger equations that have been studied by Dirk and Karen and various people, do they actually contain all the information about the quantum field theory, or are they only containing perturbative information? If they do contain non-perturbative information, is it possible to decode it? Is it possible to actually do a calculation? And how should one do that? The more difficult question that I don't have an answer to, but I would hope that I can at least convince some people here that it is an interesting question, is there a natural Hopf-Algebraic way to describe these Écarts bridge equations which relate perturbative and non-perturbative features? So I would claim that the natural Hopf-Algebraic structure of perturbative quantum field theory is reasonably well understood, although there are lots of interesting, outstanding questions still. But I claim that there should be a correspondence of that structure at the non-perturbative level also, and that there must be. So I'm going to show you a couple of actual concrete calculations, which hopefully will convince you that there is something to this. And this goes back to some beautiful old work of David Broadhurst and Kreimer and also Karen, where we can make a very concrete calculation. Now, so what I'm going to describe is a technique that will work for a set of quantum field theories, not necessarily all quantum field theories as far as we know so far, but it's a place to start. And the idea is that these people showed that for certain quantum field theories, combining the renormalization group equations with this Hopf-algebra structure leads to a very specific set of interesting nonlinear ordinary differential equations for a particular quantity that's of interest in physics, that's difficult to calculate otherwise. It's something called the anomalous dimension, If you don't know what that means, don't worry about it. It's a formal perturbative series of some interesting physical object in terms of the renormalized coupling constant. And this is an extremely difficult calculation if you just do it the normal Feynman diagrammatic way, brute force perturbation theory calculation. But using these insights from Hopf-algebras combined with these renormalization group equations, it's formulated in a way that's much easier to take to high orders of perturbation theory. And the reason this is interesting is that of all the work on resurgence in its algebraic context, its applications in various other fields, to me, the framework in which it's most clearly understood, at least to me, maybe that's my bias, is in this context of nonlinear ordinary differential equations. And so personally, I've learned a lot about this from the work of the people I've listed here, but it's a long list. And this is a field in which the ideas are well developed, well understood, and easy to implement. So let me just describe, say, one version of this theorem. So imagine you have an nth order nonlinear ODE. So you can reformulate that, recast that as a first order ODE in a vector, n component vector, I'll call Y. There's a way to cast that into a normal form. We have a linear, inhomogeneous piece, then linear pieces and nonlinear pieces. The linear pieces can be diagonalized into some diagonal matrix of eigenvalues, and then a 1 over the variable z with another diagonalizable matrix, and then all the nonlinear stuff is held here. So these linear pieces just produce exponentials. These 1 over z terms just produce powers. The nonlinear terms produce expansions in inverse powers of z here. And there are some so-called transeries parameters, which are basically the boundary condition parameters. So the formal solution of this type of differential equation can be easily written in this form. So this would be the non-perturbative terms. I've reversed here. Now z is being expanded around infinity. These would be the fluctuation terms, and these are some prefactor terms. This can be handled by Borel transform methods, and the algebraic structure of these so-called bridge equations relating the different exponential pieces. So these different formal series here are related by an intricate network of algebraic bridge equations. So this structure is well understood, well developed, and we can use this now to approach this idea of Hopf-algebras using these results of Broadhurst and Kreimer and Karen Yates. Okay, so first example. There's something called the four-dimensional Yukawa theory. And there's a certain quantity, which is the self-energy, renormalized self-energy as a function of momentum. Here's a diagrammatic form of the Dyson-Schwinger equation. This two-point function has a one-loop term. Then you can start nesting this into the propagator here and repeat and repeat and repeat. This has some nice iterative structure here. And these are these renormalization subtractions that are very difficult to implement directly at very high order without knowing about this Hopf-algebra structure. So there's a particular quantity called the anomalous dimension. It's a function of the renormalized coupling constant in the theory, the perturbative parameter. Never mind if this is unfamiliar, but it can be derived from this self-energy function here. And the nice result of this work by Broadhurst and Kreimer and Yates is that this quantity satisfies a very specific nonlinear ordinary differential equation, which for this particular model happens even to be first order. There's only one derivative, alpha, but it's quadratic, nonlinear quadratic order in the actual function gamma. So we can clean this up a little bit by rescaling the coordinate. And this is what the nonlinear differential equation looks like. It's very easy now to just put in a series expansion and generate recursively these coefficients. And here are the first coefficients. And this is in the online encyclopedia of sequences. These coefficients here actually have an interesting combinatoric interpretation in terms of being the generating function for connected chord diagrams. They also have interesting large order asymptotics. These coefficients here grow factorially in magnitude. There's also a power 2 to the n. And there's what I call a Stokes constant in terms of e and root pi, the overall constant here. And that's the leading factorial growth. There are also subleading terms. So this first term here is n minus a half factorial. There's a subleading term, which is n minus 3 halves factorial, a subleading term, which is n minus 5 halves factorial, with specific rational coefficients. But of course, excuse me, this formal series cannot be the full solution to this differential equation because there's no boundary condition parameter. There must be some boundary condition parameter for the differential equation. And this is the first sign that we need to generate, extend this formal series to a trend series. The simplest way to do that is just to take the solution to this differential equation, expand it as a formal expansion in some parameter, let me call it sigma, the trend series parameter, and just insert this into the differential equation and match powers of sigma. Extremely easy, both conceptually and to actually implement it. So we rewrite the solution as a formal perturbative series, and then what will be the first non-perturbative correction, the second power of non-perturbative correction, etc. If you insert that into the differential equation and collect powers of sigma, I think it's fairly straightforward to see that C1 will satisfy a linear equation, which happens to be homogeneous. That's where sigma comes from. And the higher powers, sigma C2, C3, etc., will satisfy some linear but inhomogeneous differential equations. And so we can just solve for C1, it turns out. This turns out to be a relatively simple differential equation. And we can solve for C1. And it's expressed in terms of C0 itself. And if we expand it in small x, we see that there is indeed a non-perturbative term. Remember, x is the small parameter. It's a rescaled version of the coupling. So this is beyond all orders in perturbation theory. It's not seen by this formal perturbative series. It has this Stokes constant prefactor, as that's part of the definition, because I can put another constant is this trend series parameter. But this exponential term is also multiplied by a formal series, which I would call a fluctuation series. So physicists would call this a one instanton factor, and this would be the fluctuation series. But notice that this C1 is completely determined by C0. It's fairly clear that how that happens from the differential equation. But I'd also like you to look at these coefficients here in the first order terms of the fluctuation around the leading exponential here. They turn out to be related to this in a very concrete way. If you remember from the previous slide, I showed you the large order growth of the expansion coefficients here. They had this factorial growth and then subleading corrections. And you'll notice that these coefficients are the same. So this is a characteristic signature of resurgent structure, that the large order growth of the perturbative coefficients here are directly related to the low order terms in the fluctuations here. And this structure continues to all orders, as I'll show. So this is one of the really remarkable, when you first see it, it becomes less remarkable once you get used to it, but also still very powerful consequences of these bridge equations connecting to various non-perturbative sectors. So we can continue, now that we have this function here with its perturbative series, which has some coefficients, we can study the large order growth of these numbers. This is a nice combinatorial exercise. And we see that these numbers here also grow factorially fast with a prefactor that is just the square of the previous Stokes constant and with some subleading coefficients. So there's an n plus 1/2 factorial growth There's a subleading n-1/2 factorial growth with a particular coefficient, n-3/2 factorial growth. The powers of 2 are decreasing 1 by 1 at each time with some coefficients. Okay, so that's the large order growth of the fluctuations here. And now I claim it should be related to this guy. So in fact, you can just, from the differential equation, you can actually derive what this one is. There's a square of this exponential term, this instanton factor. There's a square of the Stokes constant factor. And then there are subleading corrections in the expansion at small x. And again, the coefficients match exactly. And you can check this numerically to 1,000 orders if you like. It's clearly a robust structure of the equation. In fact, you can do this to all orders. We were able to extend this to all orders and write a closed form expression with all of these exponentials to all orders. So it's an exponential of an exponential generating function. And it generates the full trans-series solution to this nonlinear differential equation, which encodes the anomalous dimension expanded through this Hopf-algebra structure for this particular quantum field theory. So to summarize, there's using this nonlinear differential equation, there's an extremely explicit and simple to implement method to generate from the perturbative series all of these non-perturbative contributions of the trans series. And given the differential equation, you can do this to all orders and resum. If you're just given the formal series, then you can do this to very high precision, depending how many orders you have of this formal series. You don't need the differential equation. Okay, so referring back to this raindrop picture, what has been achieved here is C0 is the formal perturbative series. So this is a particular point expanding around the trivial saddle. And so you've got these ripples here, which are the fluctuation corrections around that trivial saddle. That's representing this. So this has some Hopf-algebra structure underlying it. And these represent the different non-perturbative sectors. These are different saddle points of the functional integral, the path integral. There are an infinite number of those other raindrops. It's a little bit like England, right, where it's always raining and there are an infinite number of raindrops. And I've shown that you can actually resum all of those to all orders from the information from the original perturbative series. So I claim that that's a demonstration that this Hopf-algebra structure here is resurrected or resurges at all of these other saddle points. And if you know the differential equation, you can just implement this to all orders if you like. So now let me turn, that's the first example. Let me turn to a second example, which has a much richer structure. And this is a different quantum field theory. This is what's called a scalar quantum field theory, a phi cubed theory, phi cubed because the perturbation is a cubic interaction term. So there's one coupling constant, which is more natural to think of in terms of A, which is proportional to G squared. So it's very simple to write down this differential equation. It's somehow characteristic of perturbation theory because it has this cubic interaction vertex. And yet this innocent looking field theory is extremely interesting for a number of reasons. It has a property which is called asymptotic freedom, which is that the interaction actually, as a function of scale, becomes weaker at short distances. And this is a feature of quantum chromodynamics, which is the theory describing subnuclear particles in quantum field theory. We'll study it in a particular critical dimension, 6-dimensional space-time, where it is asymptotically free. It's also something called a scale invariant conformal field theory, which are particularly interesting in applications in quantum field theory. It also has non-perturbative physics, meaning this is a particular field theory where we know non-trivial saddle solutions to the functional integral. So it has these different ingredients that have not been understood very well how they relate to one another. Similarly, these things called renormalons, which I won't go into, are known features of this model, and it's not well understood how these non-perturbative features interact with these perturbative features. It also has various generalizations that are of great interest in other applications. And there's been a lot of interesting recent activity extending the exact perturbative calculation to 4-loop and recently 5-loop orders, which is really heroic calculations. It's really the state of the art in perturbative quantum field theory. So David Broadhurst and Dirk Kreimer showed that in this model, there is an underlying Hopf algebra. If you combine it with the renormalization group equations, this anomalous, the corresponding anomalous dimension function again satisfies a nonlinear differential equation. It's a much more complicated looking differential equation. It's 3rd order in derivatives, but it's 4th order in nonlinearity. So at first sight, you look at this and you think, okay, that's not the way to go. But I want to show you that there's a lot of very rich structure in this nonlinear differential equation that we can decode, and it explains the relation, explains and illustrates the relation between perturbation theory and this trend series non-perturbative structure in a very nice way. So this Hopf-Algebraic nonlinear differential equation is the distillation, if you like, of these Dyson-Schwinger equations in this field theory. So we can put a perturbative expansion ansatz into this differential equation, some just formal series in powers of A with some coefficients. It's convenient to take out these powers of 6, in which case these coefficients just become integers. So that's a simple matter. You can just use Mathematica or Maple or whatever you want to put this ansatz in here, generate through a recursive recurrence relation for the ANs, and you can generate as many of these numbers as you want. So these have been inserted into the online encyclopedia. At this stage, as far as I'm aware, there is no known combinatorial interpretation of these numbers. Karen may correct me if something has happened recently. But unlike in the Yukawa case, where there was this beautiful chord diagram interpretation of the corresponding formal coefficients of the anomalous dimension, in this particular theory, this is still an open question. This is how it looks diagrammatically. Here's the 2-point function again, the 1-loop. We've got a propagator, this cubic vertex. Remember, it's a phi cube theory, so there's a cubic interaction vertex. So this is the simplest perturbative correction at 1-loop. At 2-loop, you can take one of these propagators and reinsert the same thing, and you get this. And there's something called the rainbow approximation, which I think is self-explanatory. You can continue with this rainbow term or this rainbow term, and that generates a formal expansion. There's another type of approximation called the chain approximation, where you take each of these propagators and insert itself in a sort of chain sequence. So the next one would be this one, and then the next one would be this one. So these are 2 different approximations, and they give different coefficient numbers. Whereas this Hopf-Algebraic approximation takes into account also these other types of structures. And this Hopf-Algebra expansion has this type of term, a type of expansion here. And the coefficients here are the ones that I listed here. Okay, so what Broadhurst and Kreimer did many years ago, they had less computer power than we have these days, and they studied the asymptotics of the first 30 terms of this expansion and saw this 12 to the n growth and estimated a gamma of n plus 2 factorial divergence. So first of all, it's clear that it's a factorially divergent expansion. With more data, you can actually refine this, and it turns out that the factorial growth is actually gamma of n plus 23 over 12 for some reason. I'll explain to you later where this 23 over 12 comes from. And you can even generate the subleading corrections. There's a gamma of n plus 11 over 12 and a gamma of n plus n minus 1 over 12 corrections. And by just from these numbers, you can deduce these rational numbers here in the subleading corrections. And including these subleading corrections, you see the ratio of the actual numbers to these things are extremely accurate, even at very low orders in n. So there's very compelling evidence for this just numerically from just the coefficients themselves. So let me go back and talk about this differential equation. It actually, let me also rescale just to get rid of some of these factors of 3 that are floating around. It actually, that horrible looking differential equation actually has a very nice factorized structure. It factorizes into this form here. We've got the same sort of differential equation that we saw in the Yukawa system, but with a 1 and a 2 and a 3 here. And I could handle this by a Borel transform, because now that we know that these are factorially divergent, the natural thing would be to define a Borel transform function by factoring out this factorial growth. And then the radius of convergence of this thing, including this power of 12 to the n that we observed, would be 1. And so we can relate this formal perturbative series to this Borel transform function just by a formal Laplace, order by order Laplace transform. Now, of course, the work of Ekal and Borel and company enable you to go beyond just this formal identification and to identify the non-perturbative terms with the singularity structure.
Sorry, yeah, Gerald.
Yeah.
Sorry to interrupt. I think we still see the slide with
before. Oh, okay.
Which is titled Borel analysis. So.
Okay.
Okay.
Do you see?
Yeah. Yeah. Now we see the factorization and Laplace transform. I think we're okay.
But you didn't see that before, so I should repeat.
No.
Right?
For maybe 30 seconds or so.
Yeah. Well, this is important. Let me repeat that this.
Please. Okay.
Thanks. I didn't see that. That this complicated-looking third-order nonlinear differential equation actually has a very nice factorized structure, and given that this is a factorially divergent sequence of numbers, it makes sense to define a Borel transform function by factoring out this n factorial growth. And this thing will have a radius of convergence that's finite, and here normalized to be 1. The fact that it has a finite radius of convergence means that in the complex Borel plane, complex T-plane, it will have some singularities, at least 1. And knowing those singularities amounts to knowing the non-perturbative physics, because the singularities of this function here will generate non-perturbative terms, be they branch cuts, branch points, or poles. So studying the formal series in terms of a spiral transform is one approach. But we can also use the differential equation in this case, because we have this nonlinear differential equation. This formal series that I wrote down before had no boundary condition parameters. The a and coefficients were completely determined recursively. So clearly that's not the general solution to that differential equation. So one way to proceed is just to make this trans-series type ansatz look for a solution that is this formal series plus some counting parameter, trans-series parameter, times some new beyond all orders solution. And we can just make this based on the work of these people who studied trans-series in differential equations. We can just make this ansatz that it's something exponentially small with some prefactor multiplied by some formal series. You simply insert this ansatz into the differential equation, and it will determine this for you. So the first thing you learn is that there are 3 possibilities for this parameter lambda, and they happen to be simply 1, 2, and 3. And for each lambda, there's a corresponding beta. So for when lambda is 1, the corresponding beta is minus 23 over 12. Well, that's interesting. We saw 23 over 12 in the asymptotics of the perturbative series, and now we're seeing it again in the non-perturbative solution. Corresponding to lambda equals 2, there's another prefactor power, plus 1/6. And lambda equals 3 has a corresponding prefactor, which is minus 11/4. And recall that the generic trans-series solution looks like this. It's an expansion in exponentials with the different possible values of lambda, with the corresponding prefactor power multiplied by formal series. So we can now put this into the differential equation and just generate these formal fluctuation series. So here for these 3 fundamental solutions, different values of lambda and different values of beta, there's some formal series. And here I've written the first coefficients for those first 3 formal series. So they're just some numbers. And they just follow immediately from the differential equation. Absolutely no thought involved in this. You just put it in, generate a recursion formula, and press the button. But we've seen these coefficients before, the ones I've marked here in red. If you recall, the large order growth of the perturbative series, so not these things, this thing, the large order growth of the coefficients of that thing was gamma of n plus 23 over 12. Well, the 23 over 12 was sitting here. And then there were some subleading coefficients. And this just came from the asymptotics of that sequence of numbers. Okay? They're the same numbers. Again. Okay? So this is, again, this characteristic resurgent reflection of these bridge equations, that the fluctuations around the first non-perturbative term in this trend series are related in a very precise quantitative way to the asymptotics of the coefficients of the original formal series. And since the original formal perturbative series is generated using Hopf-Algebra methods, I claim that this means that those Hopf-Algebra methods are also reflected, or they resurge in this formal series. They're just the same numbers. So we can do more than this. We can now go, now that we generated this formal series, which is the, think of it as the fluctuation series around the first trans series term in this trans series solution. So it's a different formal series from the original perturbative series. But we can now study the large order growth of these coefficients. Well, because we can generate hundreds and thousands of them if we want. It's no trouble. Well, they're again growing like gamma of n plus 23 over 12. And they have some subleading coefficients, which are these numbers here in red. They're not any of these numbers. I claim that they should be reflected in the next term in the trend series. So now we come across something very interesting about this particular model. Remember that I said that the different possible values of lambda were 1, 2, and 3. Now, in general, in a generic trend series, if you're studying a third order generic nonlinear differential equation, you will again find 3 different values of this lambda parameter. But generically, they won't be multiples of one another. They won't be resonant. They're just independent complex numbers. Okay? The fact that these are resonant means that the one here that is 2 corresponds to an e to the minus 2 over x. But e to the minus 2 over x could come from the square of this one. Okay? Because this is an integer multiple of this one. And likewise, 3 could be a product of these two. So this is an incredibly special feature. So this is very non-generic, this particular differential equation. And this non-generic resonant structure is responsible for an interesting, or has an interesting consequence. Because of that, it makes more sense to reorganize this trend series solution in powers of this exponential, because all of the lambdas here produce e to the minus integer over x. Okay, and so this solution is graded according to this exponential. And since the lambdas are not independent, we can reduce it to a single grading. So let's do that. So this is the original formal perturbative series. We just looked at this one. Now I'm going to look at this one, the next one. And the interesting thing is that this one can come independently from lambda equals 2, but it can also come from essentially the square of this one, because they're resonant. So again, it's the same story. We just throw in the ansatz and the equation spits out the solution. The solution for G2 turns out to be an inhomogeneous equation. That's because there's a G1 squared contribution, because it's a nonlinear equation. Remember that since it's a nonlinear equation, as soon as you have one of these nonlinear terms, the equation generates all of them, all multiples, all powers of those. So this is just a calculation you can do. You just throw this into the differential equation, and you learn that this is the solution. There's a new boundary condition parameter, multiply it by another series, and that series there is the one that it's the second one that I wrote down here. Okay, so that's that's this term here. But you also learn that there's a logarithmic term caused by this resonance. It's just we're familiar with this in differential equations, that if there's some resonant relation between some particular critical exponent in the system, you generate logarithmic solutions. This goes back to the Frobenius and company hundreds of years ago. But the interesting thing is that the log term multiplies exactly the same formal series as you get from this seed contribution. But there's another series which comes essentially from this thing squared. So it has a sigma 1 squared in front of it. And this thing, well, again, we can just generate the series, and here are the coefficients. And I'm sorry if this is a bit small here. I was trying to fit these big numbers on the slide. But we've seen these numbers before. The large order growth of the coefficients here of this series had this n plus 23 over 12 gamma of that, and with some subleading corrections, and these subleading corrections are just these numbers. Okay? So it really is true now that the subleading corrections to some of this G2 are directly related to the large order growth of the fluctuations here. But because of the resonant character of this nonlinear differential equation, we also see logarithmic terms appearing. So that means when you continue this to higher orders, to G3, G4, etc., eventually we're going to generate also powers of logarithms. I would hope that's clear because there's a G2 here. Eventually we'll generate a G2 squared term in the differential equation since it's nonlinear. So we'll naturally generate log squared terms. So they show up at G4 and beyond. And eventually all higher powers of log x will appear. So that means that in this model, unlike the Yukawa model, we generate a trans series that has an interesting structure. It's just a side comment. That this shows up also in the large order growth of these coefficients. The dot dot dots here actually eventually generate log n type large order growth also as a result of this resonance feature. But what this means is that this formal trans series that I wrote down that was graded according to these exponentials, remember in the first model that I talked about, this Yukawa model in 4 dimensions, that was enough. The trans series had this structure, and these things were just formal series in X. And there were relations between them, and we could resum them all. In this model, this more interesting, more intricate, more complicated phi cubed field theory in 6D, the differential equation produces a different structure. It produces fluctuation factors. So the formal series, for example, is just in powers of X. It produces multiples of this basic exponential factor, which is e to the -1 over X divided by X to the 23 over 12. This is fundamental 23 over 12 showing up in the problem. But there are also powers of logarithm of X that are generated starting here and continuing at the fourth order in this trans series expansion. Now, okay, that's interesting that it's a more general structure, and this is indeed involves the 3 basic transmonomial elements that we learned from Ekal and various people. There's this small powers of X, there's these exponential factors and powers of logarithms. But to a physicist, what's more interesting here is that this is exactly the type of trans series, the structure that you would generate if you approach this problem directly from the functional integral, just doing a saddle point expansion. The saddle point expansion would generate an expansion in this. That's this grading here. And then the fluctuations about the saddle points would generate formal series in X. And then there's something called bions, which are interactions between these different types of non-perturbative contributions, which generically produce powers of log X. So you show this to a quantum field theorist and they say, this resulted from a non-perturbative semi-classical calculation. And then you say, no, it didn't. This structure came from a perturbative Hopf-algebra calculation, which resulted in a nonlinear differential equation, which if you then study using transseries, produces exactly what you would have tried to produce if you would approach this problem from the very beginning using the ideas of saddle point expansions of the path integral. So this is an extremely explicit demonstration of this relation, these two different ways of interpreting a path integral expression for a quantum field theory. And the bridge between them is enabled by this, first of all, the Hopf-algebra structure, and also this explicit nonlinear differential equation for this particular quantity, the anomalous dimension, which you can then use to study other quantities as well. So to summarize, what we learned in this example was that there was a much richer non-perturbative structure. We could trace the origin of this extra structure to the fact that these non-perturbative exponents, these lambda parameters, happen to be resonant. They were integer multiples of one another. That was a special feature of this particular differential equation, extremely non-generic because of that, but produced more interesting structure. We saw that these relations between the fluctuations about one sector and the next sector still held, including this logarithmic behavior. So that's an even deeper type of resurgence relation. And moreover, if you wanted to, all of this information could actually have been encoded just from the formal series, even without the differential equation. It would have been a numerical decoding, but it's all contained in the original formal series. So let me conclude. So remember, my basic motivation was to try and see if this beautiful Hopf-algebra interpretation or formulation of perturbative quantum field theory and renormalization could have some direct resurgent interpretation, which would give you a link between the perturbative structure and the other physical aspects of quantum field theory. Is that quantum field theory is not just a perturbative object. It's a theory independent of using perturbation theory. It has non-perturbative features. And the question is, can you actually learn about this non-perturbative physics directly from the perturbative Hopf-algebraic starting point? And at least in these two examples that I've shown you, the answer is yes. And the answer is yes to all orders because you have these differential equations in the background. So what it means is this term here is the object in which this Kreimer-Connes Hopf-algebra structure lives, but I claim that there's a whole further structure of this thing that you're calculating, this transseries structure, and that these are all related to one another in a very nice, very explicit, very precise way, not just some arbitrary, vague comparison or relation, something very concrete. And to me, that suggests that there should be some more natural way to do this rather than using this somewhat indirect route of going through this particular differential equations, that this Hopf-algebra structure here should be reflected in a Hopf-algebra structure for this calculation or this fluctuation or this fluctuation, because those calculations themselves, calculating these fluctuation expansions, can themselves be written in terms of Feynman diagrams. The difference is that the propagators are different. The propagators are not the free propagators. They're the propagators in the background of this classical instanton field, and they're known. And so there should be some nice, again, I'm using the word natural. I don't know, I think mathematically natural way to relate this Hopf-algebra structure here to a Hopf-algebra structure for the whole transseries. And there are various other generalizations in red, which are open questions that are of interest to people in the physics community. So let me stop there. Sorry, I went a little bit over.
Well, thank you very much, Gerald, for this absolutely wonderful talk. And you were perfectly on time. We started a little bit after 3 p.m. So now we are ready for questions or comments. If anyone wishes, please.